Ideal gas Carnot engine. We wish to show explicitly that it is possible to design a highly idealized engine which can in a cycle extract heat Q from some hot reservoir A at the absolute temperature T, reject heat Q prime to some heat reservoir A prime at the lower absolute temperature T prime, and perform useful work W Q minus Q prime in the process. So um, we're extracting heat from reservoir A, temperature T, providing heat to reservoir A prime, temperature T prime. The simplest such engine is one first considered by Sadi Carnot in 1824, which operates in a quasi-static manner. The cycle consists of 4 steps which take the engine from its initial macro state A back to this state after passing through the intermediate macro states B, C, D. The engine consists of new moles of an ideal gas contained in a cylinder closed by a piston. The volume of the gas is denoted by V, its mean pressure by P bar. The 4 steps of the cycle are shown in the figure are as follows. In the first step, the engine, originally at the temperature T prime, is thermally insulated. Its volume is now decreased slowly from its initial value VA, decreased slowly, until it reaches a value VB where the temperature of the engine is T. So what kind of a process is this? This is basically what we call adiabatic compression. In step 2, the engine is placed in thermal contact with the heat reservoir, thermal contact at temperature T. Its volume is now slowly changed from VB to VC, the engine remaining at the temperature T and absorbing some heat Q from A. Well, the described process is isothermal expansion. Step 3, the engine is again thermally insulated. Its volume is now increased. Again thermally insulated, volume increased slowly from Vc until it reaches a value Vd where the temperature of the engine is T prime. Well, this is now adiabatic expansion. And in step 4, the engine is now placed in thermal contact with the heat reservoir A prime at temperature T prime. Its volume is now slowly changed from Vd back to its original value Va, the engine remaining at the temperature T prime and rejecting some heat Q prime to A prime. Well, since this is again a constant temperature process, this is going to be isothermal compression. And you can see these steps here in the PV diagram. Since it's a quasi-static process, it can be represented by a P bar V diagram. And here we see that this is the hot side, this is the cold side because the isotherm is lower. And here we are absorbing heat from the hot reservoir, and here we are releasing heat to the cold reservoir. If I use the right hand rule, I see that the area enclosed by this cycle represents the work done by the engine. So this is W, work done by the engine, because if you curl your fingers in the direction of the arrows, your thumb points into the board or into the page, which means that the work done on the engine is negative. So clockwise rotation, work done on the engine is negative. So we can see that from the P bar V diagram. And here it is represented in a schematic drawing. You see the hot reservoir at temperature T providing heat Q to the engine, the cold reservoir at temperature T prime extracting heat Q prime from the engine or absorbing heat, and W is the work done by the engine. So part A, what is the heat absorbed in step 2? Step 2, isothermal expansion. Express your answer in terms of VB, VC, and VT. So in step 2, we have isothermal expansion. Isothermal expansion in between which macrostates? We go from B to C. So we are moving from macrostate B to macrostate C. The temperature is kept constant, so T is constant. However, VB becomes VC. So that's what's happening in this process. If the temperature is constant, it's isothermal. The internal energy change, delta E bar, in going from macrostate B to macrostate C would be equal to nu CV delta T, but delta T is 0, so you find that the internal energy change is 0, which, using the first law of thermodynamics, is the heat absorbed by the engine in this process, which is Q, plus the work done on the engine, from B to C. So this is equal to 0, where the work done on the engine from B to C is minus the integral from VB to VC P bar dV. So since we have heat that is being absorbed by the engine in step 2 is minus the work done on the engine, or work done by the engine. So Q is equal to, we can see that Q must be equal to plus integral VB to VC P bar dV. And since this is an ideal gas, P bar B is equal to nu RT, ideal gas law. So if I use the ideal gas law, I can see that Q will be equal to integral from VB to VC nu RT over V dV, and the temperature was constant at T, so it's nu RT integral VB to VC dV over V. Therefore, we find that Q must be equal to nu RT natural logarithm VC divided by VB. R is our universal gas constant and nu is the number of moles. In part B, what is the heat rejected in step 4? Step 4 is isothermal compression. So in step 4, where we have an isothermal compression, we are going from macrostate D to macrostate A at a constant temperature T prime, and we're going from volume VD to VA. So that is the process. So since we have the mean energy change from D to A also equal to nu CV delta T, where delta T is 0, so this is going to be 0 as well, then the heat absorbed is basically minus Q prime, and the work done on the engine is the work done on the engine from going from D to A, you can see that Q prime must be equal to the work done on the engine from D to A. So this is minus the integral from Vd to Va P bar dV, which is, using the ideal gas law again, Vd to Va nu RT over V dV. So we find that Q prime must be equal to, well, T, I have to be careful, this is T prime, so that temperature is kept at a constant value T prime. So this will be nu R T prime, natural logarithm. Normally it would be VA over VD, but because of the minus sign, it will be VD over VA. So the heat rejected in step 4 is nu RT prime, natural logarithm VD over VA. In part C, calculate the ratio VB over VA in step 1 and the ratio VD over VC in step 3 and show that these ratios are related. Okay, so in step 1, we have adiabatic, it was adiabatic compression, and in adiabatic processes we have we're going from temperature T prime, so the macro state A is temperature T prime, volume VA, we're going to temperature T, volume VB. So since TV to gamma minus 1 is a constant, T prime VA to gamma minus 1 is T VB to gamma minus 1, where gamma is CP CV, CP over CV ratio. In step 2, in step 3, we have what we called adiabatic expansion. Adiabatic expansion. We're going from TVC to the macro state D, which is at T prime, temperature T prime, VD. So we have therefore TVC to gamma minus 1 is T prime VD to gamma minus 1, since it's an adiabatic process. So if I write these once again, first I had T prime VA to gamma minus 1. This is equal to T VB to gamma minus 1. And here I have T VC to gamma minus 1 is T prime VD to gamma minus 1. So if I write this here, T prime VD to gamma minus 1 is equal to T VC to gamma minus 1. You can see that the T primes will cancel and the T's will cancel, and I will find that VA over VD to gamma minus 1 is VB over VC to gamma minus 1, or VA over VD is equal to VB over VC. So this is the relationship between the volumes. Part D, use the preceding answer to calculate the ratio Q to Q prime in terms of T and T prime. Okay, now Q over Q prime. What was Q? We calculated in part A, nu RT, natural logarithm VC over VB, and Q prime was nu RT prime, natural logarithm Vd over Va. So the new r's will cancel, and Vc over Vb is Vd over Va, or Va over Vd is Vb over Vc. So these two will cancel as well because they are the same thing. So I find that this ratio Q over Q prime is T over T prime. Part E. Calculate the efficiency of the engine and show that it agrees with the general result for a quasi-static engine. The efficiency of the engine is the useful output, the work done by the engine, divided by the amount of energy we are providing into the engine, it's Q. And W we have shown to be equal to Q minus Q prime, and that's also in the problem statement. W is Q minus Q prime, so it is Q minus Q prime divided by Q, which is 1 minus Q prime over Q, which is 1 minus T prime over T. So the efficiency of the engine is T minus T prime over T. And this is actually the maximum efficiency allowed. This is the maximum efficiency allowed for a heat engine by second law of thermodynamics, as we have shown in our lecture. Okay, so it is in agreement. So we walk through the Carnot cycle. First we see that we have 4 steps: adiabatic compression, isothermal expansion, adiabatic expansion, isothermal compression. Isothermal steps are at temperatures T hot, T prime cold, and adiabatic processes take us from T to T prime and T prime to T. And for adiabatic processes we can use TV to gamma minus 1 is a constant, or PV to gamma is a constant. And for isothermal processes we use the fact that the internal energy does not change. So in the first step, using the isothermal expansion, in the second step, we use the ideal gas law in combination with the first law for a zero internal energy change. The heat absorbed by the engine is minus the work done on the engine. So work done on the engine is minus integral P bar dV. Work done minus the work done on the engine, or work done by the engine, is plus P bar dV. And that gives us our result. In step 4, isothermal compression, we have the reverse situation. The Q prime, the heat released by the engine, is equal to the heat absorbed, is the work done on the engine, WD to A, so it's integral P bar dV. And in step 1, adiabatic compression, we use TV to gamma minus 1 is a constant, and also in step 3 to find the ratio VA over VD equals VB over VC, or this can be written as Vc over Vb is equal to Vd over Va, which is what we needed in part D when we looked at the ratio Q over Q prime and showed that it is equal to T over T prime. And efficiency, the useful output of the engine, work done by the engine divided by the energy that we provide, that is heat Q, is 1 minus T prime over T, and which is indeed the maximum efficiency allowed using the second law of thermodynamics.